Um, Hello, everyone. I am Yamina Itamer from French National Research Agency, ANR, with my colleague Margarita Prado from FCT Portugal. We are co-chairing a working group on greening research. And in this context, we welcome you all to this Science Europe webinar, to the second webinar on the specific topic of greening digitalization. So I would like to welcome our two speakers, Adel Nourdine and Ruggero Ricci. I will introduce them later as soon as everyone is connected. I don't know if we can start or not yet. We have 39 participants already registered, connected, sorry. Okay, let's start. So our two speakers, two distinguished speakers today are Adel Nourdine. He's associate professor at University of Pau in France, and he's one of the pioneers in the area of measuring the carbon footprint of green computing and a pioneer in green digitalization. And the second speaker is Ruggero Ricci from the Italian National Institute for Nuclear Physics. And he is going to deal with all the greening aspects related to heating equipments. So just some information related to how the webinar will run. We will have the two talks, consecutive talks, no questions in between, and we will allow for discussion and questions right after the talks. They are expected to be 15 to 20 minutes each. And then I ask you to ask your questions, to write your questions on the chat. And in case your question is specific to one of the speakers, so please mention in the question to which speaker your question is addressed. So I think we can start now. I will stop sharing. And Adel, the floor is yours.
Okay, thank you. Let me just share my screen. Okay, thank you, Yamin. If we are good to go. Yes. Okay.
Yeah, it's fine.
Okay. Thank you, Yamin, and thank you for inviting me for this webinar. So I'm Adel Nourdine, and I'm an associate professor at the University of Pau and Pays de la Dour, and I'll be talking today about the impacts of the energy and the CO2 impacts of ICT in general, and how this impacts research, and how can we measure the impact of research. So a little bit about me. I'm an associate professor. I work at the LUPA laboratory, which is the computer science laboratory in Pau, in southern France. I'm a researcher in green IT. I started working on this topic in 2010, in particular in the areas of software engineering and autonomous computing, mainly in how to measure the energy consumption and then the environmental impact of devices and software and source code, line of code and software, and how we can manage an ecosystem of devices and software to optimize the energy consumption. So that's broadly my research areas. So you have my website with all the details and different projects and publications. So before talking about some numbers and what's the impact of our software and devices and research, to put all of this into perspective, it's interesting to see where is my mouse? Sorry, it's interesting to set the context where what you see here on the graph is what we call the Kondratiev waves of innovation. It shows that throughout history there have been waves of changes, new innovations that have changed our societies and our civilization and our industries. So in prehistory, we used to transform material, and this is where we have, Stone Age and Bronze Age and Iron Age. And with every innovation in transforming material, it had a lot of impact on our societies. And then since the Industrial Revolution, we started transforming energy. So from water power to steam power to electric power and combustion power. And each of these waves had its fair and share impact on our societies. And the last wave of innovation is what we call the communicating and storing information, which we are still living in it since the end of the 70s and early 80s. This is what we call the information age, where we communicate a lot, the internet and all the computing devices we have. We communicate, generate a lot of information, and store this information. Now, the next wave of innovation, which supposedly we're starting in it, is computing information, is where we use this knowledge and this information and all of this data we generate to compute it, to calculate it, to extract new knowledge from it through software and algorithm. Now, why this is important? Because this new wave of innovation through transforming information doesn't come cheap. It has an impact that other waves had in the past, and it has a big impact because when we talk about algorithm and generating new knowledge, we talk about a big ecosystem of devices and networking and data centers and data, which I call software ecosystem. So it goes from sensors, Internet of Things, IoT objects and devices and sensors, which we have everywhere, billions of these devices, hundreds of billions of these devices. And they all collect data, generate data, do some processing, and then send and store this data in big data centers and server, which also had a lot of computation and calculations happening in it. And everything in between is also part of this ecosystem. So all the other devices we have, like computers, smartphone, etc., but also us humans and we are actors in this ecosystem. So end users, but also developers and managers and administrator. And what binds this ecosystem together is software. And I like this this quote from the Software Heritage Foundation that says that our lives and our industry and our whole society depends on software. So this dependency, so I wanted to show these two graphs just to show that this dependency to software and computing is part of this new wave of innovation, and we cannot just get out from it. But it has a big impact on the environment and on the climate. And this impact is not negligible. So ICT impact in general, we know a few numbers. It used to consume 7% of the total electricity in 2020. So these numbers were much less in the past. As you can see in this graph, it's increasing and it's increasing even more and more. We expect it to be 30% on average in 2030. And the numbers will vary. You will see different numbers, 30%, 20, 15, 12, because it's quite difficult to get correct estimates. But what's important is this energy consumption and electricity consumption is rising. And as you can see, it comes from networks, from data center, but also from producing ICT devices and from consumer devices themselves. And we have the same impact of greenhouse gas emissions of ICT, which used to be around 2%. The carbon footprint used to be 2% in 2007, and the number is expected to grow up to 14% in 2040. So today we are, depending again on the estimates, we're around 7-8% of the entire planet's CO2 emissions is due to ICT. And I can show you a little bit more detailed graph, like with some estimates, whether we apply some conservative growth, or we apply some sobriety and approaches, or we keep it as is. So these numbers are from the Shift project. But again, it shows that there is an increase, and this increase will continue in the future. So the part of ICT in the total total energy consumption of the planet. And we have similar numbers in this graph for greenhouse gas emissions. So again, we're around 67% today, and these numbers are expected to grow. And these numbers are growing even though we have more energy efficient devices, more energy efficient policies. And you'll see at the end of this presentation why it's still growing, even though we have better computers today and better servers. Now, this impact is not only from the use phase. Is if you see this graph, which if you see this graph, which decompose what's the ICT or carbon footprint of between the production phase and the use phase. So before having our devices in hand, there is nearly 40% of its carbon footprint already consumed from from producing these devices, and then the rest from using it. So the production phase is as much important to optimize and to reduce its impact than the usage phase also. Now, these numbers, again, are not going to go down because we have more and more, we produce more and more of these devices. And this is where the next graph shows is the evolution of connected devices worldwide. And these numbers are going up. Now, hundreds of millions, billions, and dozens of billions of devices being built, produced, many of them in automation, many of them in IoT devices. So every one of these devices need to be built, need to be shipped, need to be installed, and obviously need to be used and then recycled at the end. So there is, we are dependent on ICT. We use more and more devices, build more and more devices, and that impact is not negligible at all. Now, if we check these devices to see, in particular, what's the distribution between use phase and production phase. Now I show the number overall, but if we check device per device, we will also see that there's a lot of disparities between each device. So here I have 4 examples of 2 mobile phones and 2 computers, and depending on what device we're using, the impact of production might be higher or lower. So for these specific devices, the production is more than the majority of its carbon footprint. So for instance, the iPhone 12, 83% of its carbon footprint, the embodied carbon footprint is from its production. So whatever optimizations we do on software or on how we use these devices will not be enough to reduce the overall impact. It's important to think whether we need to build a new device, to change our devices frequently. And what we see in consumer devices, we see it also in industrial settings, particularly in data centers, where there is a refresh rate which need to be as important as the use phase. Now, all of this production, why it's important, because if we check the life cycle of a classical smartphone, so there's all the different phases to build a smartphone. It starts from raw materials, extracting rare earth mineral and metals, which are needed to build the modern smartphone or any modern computing device. And there's a lot of CO2 emissions and energy consumption happening at this phase, just extracting these materials. So a lot of different mines and different, and these materials are not necessarily in the same location in the same country as the production phase, as a factory. So you have the raw materials, which need to be extracted, then need to be shipped to the manufacturing and to the factories, which will build the devices, and then the manufacturing and packaging and distribution by itself. It's estimated that it will consume nearly half of the energy of the total lifespan of a device. So all of this have an impact. Just before arriving to the use phase, we already spend a lot of energy and CO2 emissions in extracting material and building and shipping the device. And then finally, we have the use phase. But again, when you use an end user device, a computer or a server or a simulation device somewhere, the energy consumed by the device itself is obviously is important, but these devices are connected and they are today useless without all the infrastructure behind them. So when you use an application on your phone, usually it's connected through mobile network towers, through different networking equipment, and it connects to server-side applications in data centers, in big servers and data centers, which have a huge impact. So the usage phase is all of this together for a seamlessly simple device. And then at the end, there is the recycling and the end of life of devices, which in many cases are not even recycled. But even if we recycle them, they have they have also an impact in energy and CO2 emissions. Now I'm showing that because if we check what's in a modern smartphone. So the idea is not to go into detail, but to show that every component of a modern smartphone uses some minerals, some rare earth metals that are really critical to build these devices. So, lithium for batteries, we need indium for touch screens, and etc. So we really depend on these rare metals, to build our ICT devices. But these rare metals, and this is the ones in the periodic table that we really use to build our devices. So these rare metals, there's two issues with them. The first one is their recycling rate. And as you can see in this graph, their recycling rate is very, very low. Most of them are not even, below the 1% recycling. So we don't recycle these metals. And they are finite number of these metals. And the second issue is that they're not available everywhere. So there is a few select countries that have most of the mines and where most of the extraction of these metals is happening. So there's a lot of other geopolitical and economic factors happening. And many of these rare metals are specifically extracted to be used in ICT. So this graph, 10 years old graph, but still valid today. Majority of, say, gallium or indium is extracted and is used specifically in ICT. So if we're not using them in ICT, we would not be extracting them. Even gold, which is the last number, the last graph here, gold, a big chunk of it, a non-negligible part of worldwide gold is used in the ICT industry. So that's real cost behind ICT. This is the just even before actually shipping and using our device, we already spend a lot of energy and CO2 emissions on that. Now, what we did here in the hardware side, where we tried to analyze the entire life cycle of devices from and on ICT, from rare earth metals to manufacturing to shipping to use phase, we can do it also for software. Now the software side for applications is much more difficult to estimate. So if you're running, I don't know, a large language model like ChatGPT or Earth simulation or climate modeling, that's software running. That's software running on some data. But what's the impact of that software? And what's the impact not just on the use phase but the entire life cycle? So this is a new research trend. Not a lot of research so far. We don't have enough results so far, but some of the results is what you can see in this graph. If I have an idea of an application, and from having the idea until building the application, what's the impact? What the entire impact? Now, this is a study by some colleagues who tried to estimate what's the impact of people that need to transport to go by their car from their their home to the office, and then build, write the software on some laptops and computers, and then there is storage all of this data, which again have an impact. Again, if you want to build, you go to the office, there is an impact of the office itself, lighting and ventilation. And what it shows that the energy consumption and the carbon footprint specifically for data center, and when you build and deploy your application on data center, is a minority of the entire life cycle impact of software. So even for software, the impact is again diluted in the entire life cycle. And one thing we need to be aware of and to take care of is two big problems with, if we manage to measure everything and optimize everything, is first is what we call transfer or pollution transfer, or transfer of energy and CO2 emissions. So even if we improve our manufacturing processes, if that means we need to have more raw materials or more difficult to extract raw materials, and it's more difficult to recycle, then we didn't gain anything overall, because we just transform it from one phase to another. And this is what we see a lot in computing today. We see a lot of this transfer. And the second thing is about the rebound effect, or the Jevon paradox. So if we optimize our application on devices and software, we end up using them more because it costs less to operate. And at the end, we are consuming much more CO2 emissions and energy consumption. And this is what we're having today in computing. This is why data centers are consuming much more energy than before. Computing is energy and electric energy, and CO2 emission is rising because we are using them more and more. This is the new wave, cycle of innovation we're living today. And I do think we still have a lot of optimization to do. And just a small side note here, there is a medical doctor who tried to do an analogy between how much us humans we need to survive in terms of energy and how much a light bulb consumes. So he calculated that us humans, from calories converted to joules and watts, we need the same amount of power as a light bulb. So 120 watts, that's roughly what a GPU running, at low performance. So if you want to run, the new ChatGPT model, it will consume much more power compared to what a human does. Even though we are much more dependent, we're much more complex. So it means there is still a lot of margin of improvement and optimizations in our ICT devices. And so a few numbers about LLMs and AI, because I took this example to compare to humans. There is nearly 10,000 data centers today, and this number is growing, and its electricity consumption will double between 2022 and 2026. So nearly 1,000 terawatts in 2026 for data centers, mostly due to the shift in needs, dependency on these data centers, specifically because we're using more and more AI and large models and storing much more data on these devices. And the impact is not just energy consumption or CO2 emissions, but also water consumption, which is also increasing in the data centers. So for instance, for Google and Microsoft, 20 and 34% increase in just 1 year between 2021 and 2022. So that's one part of the explanation of the Jevon paradox, where we're building more efficient data centers and devices, but we're more and more using them. Now, in terms of research institutions, so all of this ICT impact worldwide is big, huge, important. But in academia, we often tend to not measure what we're consuming. On average, the research facilities, they consume more energy than traditional commercial buildings. It's mostly due to the equipment we use. If we have like electron microscopes or freezer or fridges in biology, let's say, obviously all the IT equipment, the ventilation system. So we use a lot of electricity, and therefore also we emit a lot of CO2 emissions. And there's there's a report which suggests 4 recommendations, and rising awareness. So let's say we turn equipment off when we don't use them. Automation. We use some automation and some sensors to detect when we can turn off some equipment. Better reorganization, so of equipment use, so we can schedule better how we use equipment. Some equipment needs will consume more if they turned off than turned on frequently. And finally, to produce local energy production and use of renewable in research institutions. So these are 4 recommendations that are recommended by this report. And if you see, none of them is about IT directly. None of them is about optimizing the equipment themselves or optimizing software running of them, because this is not where most of the improvement will happen in these institutions. So for instance, just a side note also, this is, I have one slide more. So for instance, in a lot of scientific fields, when we want to build large language models or climate models or Earth system modeling, we will be using a lot of data and a lot of computing power to calculate and build this model. And we will be using a lot of data, so in megabyte, terabyte, even petabyte of data. So today, the scale of data means that it's faster and more energy efficient and more CO2 efficient to transfer our data, let's say, for example, 100 petabyte of data through a physical truck than over high-speed fiber and optic networks. So there's an anecdote with Amazon AWS have a Snowball truck and Snowball service, which is a big truck, a huge truck, which had a lot of IT equipment in it, a lot of storage equipment in it, and it will drive to the data center location. We will copy the data to the truck, so 100 petabyte will take maybe a week to copy, and then it will drive, consuming oil and diesel to the client's location, and then copy the data back. That will be much more energy efficient than copying through high-speed fiber network, because 100 petabyte will take around 20-25 years to copy on the highest speed network we have today. So this is the scale, and this is where we need to think about outside the box solutions. So it's not enough to think about a compression algorithm and then to send the data through high-speed fiber network. And just to end, as I said, we do not measure a lot CO2 and energy costs of our research activities. They're not always measured. They're not always added to research institutions' global impacts. If you see some universities' impacts, usually they will not measure or include what their research activities have estimated, have consumed, because it's very, very difficult to do so. Many of the computing infrastructure is actually shared between different projects, different institutions, sometimes between different universities and different cities. And in many cases, specifically in computing, we do not have our own infrastructure. We rent it from major providers. So we rent some space in Google or Microsoft cloud rather than building our own data center in-house. And many of this infrastructure is not always fully used. So one report says from the Uptime Institute, 25% utilization today of the of data centers, of the CPU and GPU of data centers, 25%. It used to be 5% 10 years ago. So there is reasoning, commercial reasoning why they don't go up, but it's still very low. And finally, there is the issue of return of investment in cost, emissions, and energy of research itself. So if I build a new climate model or a new estimation model for some of behavioral patterns of fish, the return of investment, social return of investment, will not be in 1 year or 2 years. Maybe it's 10 years, maybe in 50 years, we will have some return on investment. So the scientific impacts are on the long term, but we are consuming energy and CO2 emissions today. So this is why it's really difficult to even if we manage to measure how much we emit, it's really difficult to say whether it's good or bad, or whether it's high energy consumption, low energy consumption.
Adel,
yes, and that's it.
Thank you.
Sorry.
Thank you. I just wanted to ask you to leave some time for the discussion.
No. I know I crossed the time. Sorry.
Okay.
So that's it for me.
Thank you, Adel. Thank you. Very interesting. I think we will have many questions related to that. So, no loss of time. I will get back to Ruggero.
Okay.
Okay. The floor is yours.
Let me share. Can you see?
Yes, fine. You can put it full screen now.
Hello, everybody. My name is Ruggero Ricci.
Ruggero, can you put it in full screen, please? Oh, fine. That's well. Sorry.
I'm from National Institute for Nuclear Physics. My lab is in Frascati, close to Rome. The National Institute is devoted to study nuclear and subnuclear physics. Of course, I'm not a scientist. I'm only an electrical engineer. But I'm going to share with you some activities that could be useful maybe for other situation. Our labs is here in Frascati, close to Rome, and is devoted historically to the study of particle accelerator. Since the end of 50s, we had a long tradition in electron and electron-positron collider. Now is running in Frascati, is still running Daphne, that is electron-positron collider that I will show you in a few minutes. And Spark, that is a linear collider devoted to study at the beginning the free electron laser effect. Now is used to study the plasma acceleration, and is going to be prepared to develop terahertz radiation for matter study. And now we are pushing on our attention to a new particle accelerator named Eupraxia. That is a European project. This is an outlook of our campus. Is big, large. 4,400 people is working there. You can see that there are several research infrastructure, mainly Daphne, Spark, and other facilities. But we have also a data center, 200 kilowatts of IT devices. And a new one is under construction in 2 years, bigger, 1.2 megawatt. I'm involved also, I'm electrical engineer, involved head of electrical department, so I'm involved in the electrical distribution from the high voltage to the low voltage, and the accelerator facility by the point of view of power. I'm also the energy manager, and I take care also of the electrical and power about the data center. So this is an outlook from the satellite of our campus, and this is another outlook seen by the energetic point of view. This is an historical trend of year by year energy consumption, where you can see 2 different colors, because I used to divide the energy used into family. The blue one is the energy due to the base load of all the labs, and the green one is, and the orange one is that due to the accelerator. So it changes, of course, by depending on the number of the days every year, but also it changes because we reduce the power need. So I would like to stress that it's not really visible, but you can see that the blue line is decreasing from 10 gigawatt hours per year to about 8 in 10 years. So we reduce it about 20% in 10 years, our base load. This with several activities, but also with a small change of behavior. So we can say a small sobriety in terms of everybody behavior. About the natural gas, you can see that the trend is decreasing hugely. So in the middle, you can see that we have a big reduction due to the introduction of the waste heat recovery system that I will show you is the item of our talks. I would like to stress also the trend of the cost, the global price of the kilowatt hour, because in my opinion is the best drive for the energy awareness of the people. So the peak cost of 2022 was 3 times of the regular one. So everybody now is engaged to look with more attention to the energy. 1 minute about Daphne, that is our big particle accelerator. The aim is to produce a collision between electron and positron at 510 MeV, but I will not talk you about the accelerator, but only about some activities that can be studied. Daphne is a very crowded accelerator full of magnets, power converter, and radio frequency power station. It's as usual in a particle accelerator, is very power demanding. At the origin, we have a load of about 5.9 megawatt, and it runs usually for 6,000 hours. So you can guess that it's very expensive and it's a very big impact in terms of environment. Now we reduce the power demand with several activities. I will show you only two activities, because in this period, 2007-2012, Daphne was renewed in some part in order to arrange the interaction region in order to obtain the crop waste compensation. That is a new way to of a more efficient collision between electron and positron that was studied here in Frascati. And during this upgrade, some activities has been studied in order to better some components. And in this activity, in this framework, some work has been done also in terms of energy saving. I will show for Daphne, the main users are magnet power supplies, and on 2 of these was done a big work, a big job, and I will show only this in order to explain that in order to better the field properties of the magnets and better the efficiency, the effect of these components that is very power demanding. There are 8 Wigler magnets with a power of 250 kilowatts each. Some modification has been introduced in order to better the magnetic field, and they accepted to reduce also the gap that impose a higher current. So we are now running a small modified magnet with saving 1.7 megawatts that are a permanent reduction. So it's the cost was very low. Maybe the return of investment was about some weeks. So the second activities was done with my contribution is related to auxiliary cooling system. So you can imagine that if we have 5.9 kilowatts from the network, you have to dissipate the same as heat. So we have industrial cooling plant that was a bit aged. So the first aging is on the control system. In my experience, I can see that the obsolescence of control system is much faster than that of plants. So we had a lot of fault on this plant that was the motivation to review all the system, in particular the control system. I proposed to have an approach of study as an internal reverse engineering study. So it was very fruitful because internal engineering engineer has year operation, maintenance, and fault experience to take into account. We performed a need analysis review because with respect to the original design, you can have many changed and new different needs. It's useful to have a quick calculation sizing in order to review some initial choice and eventually resize some part of the plant. It was an opportunity to share experience and request with all the stakeholders, so technician and operator and physicist, and the opportunity to implement new generation devices in terms of control and regulation. So the effect was that at the beginning we have in this case, 3 cooling tower running at the maximum power for all the time in order to obtain a sustainable system. Now we are using only the number of tower requested to cool the amount of heat at the moment with respect to the environmental condition. So we have overall reduced the power demand of this kind of installation of this plant of about 50%. But the item of today is the data center heat recovery system. I proposed this idea first time 2012, so more than 10 years ago, in one of the many call for green data center as a marginal activity. At the moment, I propose to renew the cooling system, the chiller system, using heat recovery system new chiller. But the project, of course, was rejected because it was in the mainstream. but we deep into this item with some colleagues, and we started that was possible reuse, modifying the existing system with small changes, and our director approved the small cost. So in 2015, we had the deployment of the new layout, and we started the commissioning, starting to use this heat recovered since winter 2015. So we have we have 9 years of experience. Why doing it in Frascati at LNF? Because it's easier, because we are in charge for the cooling of the data center, because it's our data center under our responsibility. Because we are under our responsibility also the heating, and we have an existing district heating network. Also, we had more or less all the building that we are supplying with the heat was cooled with refrigerated in summertime with fan coils that are sized also for winter season. So the last things we think was that our chiller, water refrigerated, could increase the condensating water temperature up to 45 degrees. So there are all the conditions to try it. So the principle is this. We have a data center that is a permanent load. We supply, for instance, 200 kilowatts to the data center. We have to remove it, and we have to spend buy a chiller in order to cool it down. In our case, our chiller substation was devoted also to other permanent loads. So the principle is the same. You have to remove 400 kilowatts. You spend to increase the temperature, and you spent electrical energy to increase the temperature and to waste this heat, adding the power, electrical power. So if you have 400 kilowatts, you have to add the electrical power due to the compressor cycle, and your result is you have to remove 490 kilowatts that you spend to remove using, in our case, cooling tower, and you waste it, and you say, oh, you have 490 kilowatts, and you have to waste it, and you say, what a pity. But you are wasting it, you are removing at 28 degrees, that is a very cool, is not very useful temperature. So the idea is, if I increase the temperature up to 45 degrees, 40 degrees, I could use for the heating. And we studied it, we simulated the situation. So on the left side is the same. In the right side, you can see that we have 42 degrees, that is useful. In order to increase this temperature, you have to spend more electricity, 21 kilowatts more, but you have available 400 kilowatts available for district heating. So we have 400 kilowatts spending 20 kilowatts more. So it could be very cheap. Of course, what you don't use for district heating in a moment, you have to waste as balance power. Here is briefly our network existing and with some extension. We are supplying 11 buildings about the 40% of our building in terms of cubic meter. And so we serve about 250 people heated by this system. 9 years of experience results in terms of energy supply, thermal energy supplied, and on average we have supplied more or less 1 gigawatt per year. So we can evaluate the environmental result, and if balance the avoided usage of natural gas estimated with a conventional efficiency, and the additional current, the additional power used for increase the temperature, you obtain that you have this result. So we can say that you are saving 140 tons of CO2 every year. Limits of this pilot plant. Of course, the solution was based on existing chiller and the hydraulic equipment that are not optimized. This system implies a configuration named total heat recovery. So, as you see before, if you have to increase the temperature of all the power, may also if you use only a fraction. So you starting to do this by scratch, you can use other configuration, but the result is the same, is useful to do it. In the near future, we are going to start the construction of the new data center, and 600 kilowatt will be used as heat recovery with, of course, a new and more efficient configuration. Not more than this, because we are finished the building to heat. But to use this power, we will have to extend the heating district heating system. We have also a project that is under installation of 1 megawatt of photovoltaic fields, but is not in the development. So, keywords of our experience. Allora, a data center is a cheap and reliable heat source. In the previous presentation, we saw that the data center will use a very big slice of total power. So we will have a lot of power from the data center, the thermal power. So data center is cheap and reliable heat source. In our research institute, or like us, we have also other heat source, but not reliable as data center that is at the steady state for all the year. The second keyword for me is that heat recovery is not the same of a conventional boiler. That means that if you want to use energy recovered with an efficient system, you have to think to use low temperature devices. So it's recommended to use less than 50 degrees. Otherwise, you spend a lot of energy in order to increase the temperature. That is not convenient. The maximum is not a boiler. The consequence is also that the maximum exploitation is using this system as a base load in case you can integrate with conventional sources. The heat recovery is for free, so when available, so you can change your mind timing and parcelization during 24 hours in order to avoid peaks of demand, power demand during the day.
Ruggero,
Yes.
are you set? Are you set, or we are running out of time? Can you conclude, please?
Yes, yes. I mean,
Okay.
the last thing is that the reuse of data center waste heat is being introduced in the best practice of European Commission. This work was done using joint activity from our internal department, technical department, and this was very useful. I'd like to place in your thoughts this in I'd like to place this in your thoughts, this observation. The research labs are good environment to think, develop, and test unconventional solutions. Sustainability upgrades sometimes can be obtained with limited modification, but they take little courage to change what works. Usually, from time to time, needs analysis review is very useful. This kind of improvement can be performed only with the skilled technical staff. It's difficult to do the same using external people, taking advantage on experience and interaction with all the stakeholders. Last things for European communities that unfortunately many funding system point out to pay for goods, not for scale. Okay, thank you for attention.
Thank you very much. I will use the rest of the time, even if it is not too much, to take some questions. There are many questions on the chat. So the first one is to Adele. How does reuse or sharing of equipment impact the production and utilization of devices' carbon footprint? Is there an impact on the use? And is there any circular economy study on the reuse and sharing related to the equipment? This is for Adele.
Okay, thank you, Yamin. Thank you.
Very quick.
Very quick. It's a good question. So I mostly work on the use phase and software engineering. So off the top of my head, I don't have reliable sources to give you directly, but obviously if you reuse or you share equipment, you'll avoid building a new one. So there is some economies overall in the life cycle. There might be some studies. I don't have any in my top of my head. Just run out to give you quickly.
Another question. Yeah, sorry. Can you recommend a tool to effectively measure energy consumption of devices, or should we focus on the product of carbon footprint to measure the CO2 impact? Are there tools that allow you to make this measure, or shall we measure just the emission of carbon of CO2?
So I have I built some tools in a project. I know some of colleagues have built some tools to measure the energy consumption of electric energy, either directly or through a model and approach. So you can check our tools specifically in a Joule project. We have a project called Joule project, and there's a few others that I know about. But they don't measure CO2 impact. So for CO2 impacts, there's a few estimation models that will try to integrate all the life cycle of devices. So mostly you will see mature models in data centers and servers. So from the Uptime Institute, I think from the University of East London, they have a few. In France, we have the Boa Vista project, which and the Shift project, would have some of these approaches for the entire life cycle.
Can you repeat the first project you mentioned?
My project is a Joule project, Joular. It's on my website. If you check Joule project, it's mostly for software and computing devices, from IoT to devices to computer and servers, and it will measure the energy consumption from hardware up to source code. I'm not sure if I put in the link or if everyone will see it, but I'll try to put it in the chat.
Okay, in the chat, or people can contact you even.
For
yeah, it's so another question to all the panelists, which says maybe we can give the floor to Rogero. Could you please recommend a good tool which is being using for scope the emission recording?
Ma emission recording, allora, emission are CO2 emission is estimated, evaluated using supply chain because or other system. So you don't measure CO2 emission by measuring the CO2 out of a pipe. You can study the contribution in order to produce every goods. For instance, energy, electrical power. Electrical power, there is a conventional parameter that tell you how, on average, how much CO2 emission you have for each kilowatt hours. And the supply chain studies the emission related to the production, maybe of a chip, of a component. So all the, in Italy is filiera, all the path of the production of a good has to be registered and have to take into account the amount of CO2 estimated for each level. So transportation, study, development, and production, and so on. For a data center, for me is easier because I have only one parameter, that is the electric energy usage. So I have only to multiply the CO2 equivalent of my electrical power supplier and obtain the amount of emission. I can choose to change supplier or to produce an electric energy by renewable energy. So in this case, I reduce the impact. So this is, I think, the usual way to do it.
Okay, maybe we can close with a last question, which relates to the activities of Science Europe. How can you relate the challenges that you have mentioned on both on the software side or on the electric power plants? How can you relate these challenges that you have mentioned to the case of research funding or research performing organizations? For example, in the case researchers perform some projects or funding agencies do some projects. Do you have any ideas how we could relate this to the research activities?
So do you mean so do you mean about what research agencies have an impact? I mean, how can they judge research projects, whether they should integrate, energy in, as one parameter in judging research projects or funding them, maybe in this sense?
Yeah, for example, this could be this.
Well, I mean, the difficulty is that research, specifically if we're in the low TRL, low maturity, if it's really if you're exploring early on research and ideas, the return on investment is the long run, on the long term. So yeah, we might consume a lot of energy today, but maybe the benefit will be huge in 20 years. So it's difficult to just add a metric saying I will fund projects that will consume no less than X CO2 emissions or X joules or watts.
How about you, Rogero?
It's not easy. Yeah.
Rogero, do you have any opinion on that before we close?
Research Institute, also particularly high energy physics European community, is the power demanding. So there is a commitment for several years to reduce the impact in terms of sustainability. In terms of sustainability, by the point of view, the reduction of the power demand, reduce the emission. It is not only by environmental point of view, is an economical needs. Otherwise, you don't the power expenditure is very high, so a facility is not sustainable by the economical point of view. And it's very useful. It's very committed. So I'm participating to a lot of meeting and activity of this kind of research institute aimed to reduce the impact both in the conventional users, but also for the research devices. On September there is a new one meeting in Madrid, if you want, Esprit.
Thank you very much. So I think we will close now the webinar. I would like to thank you on behalf of Science Europe. I would like to thank the speakers and all the participants who have provided some questions. Many thanks. I think we can close now, Nicola, if you agree. So thank you very much again. Thank you. Bye-bye.
Bye-bye.
Thank you.